Hey guys, so in this video we are going to solve the Schrodinger equation actually for a particular situation. So the situation I want to set up, and remember our situation is going to be defined by the potential energy function. And actually, before I do this, I want to remind you, if you have not reviewed the differential equations video or the video on complex exponentials, that material will be incredibly useful in this video. And I will reference some of what we did in those videos. Okay, so the potential energy function that I would like to work with today, it is called the sometimes called the the infinite square well, and oftentimes also called the particle in a box. Which the square well sometimes doesn't make sense because we are working only in one dimension, but you can think of it like a particle trapped sort of in a one-dimensional box, and you'll see what I'm talking about, where we have a potential energy function that looks like this. I'll explain this in a second. Those should be straight lines. Not great at drawing straight lines, apparently. So this is x equals 0. Redo that. This point over here is at x equals 0. And this point over here is at x equals a, right? And inside here, between x equals 0 and x equals a, we have the potential energy function equals 0, okay? And since it's flat, that means there's going to be no forces acting on the particle. Outside, though, we are at potential energy equals infinity. Remember, particles try to escape potential energy, right? And these, vertical lines actually means that we're going to have forces, an infinite amount of force, and particles resist high potentials, right? That's the idea of potential energy. And so, in fact, what we have in this situation, if we model the potential like this, we have a situation where a particle is free to go anywhere between x equals 0 and x equals a. The particle is free in here, but outside the box, the particle cannot be there, right? And we can actually put some conditions on the wave function right there from that, where we don't know the wave function between 0 and a, but we know that psi of x being less than 0 has to be equal to 0. Right? That just means when we, take the norm squared, right? And the wave function, any wave function, cannot exist outside of this. That would mean that there would be a chance for the particle to be in this infinite potential energy area, and that can't happen. Similarly, psi of x greater than a has to equal to 0. And we can actually go one step farther, right? Which is, think about what happens at the walls, right? You can imagine a particle bouncing back and forth between two walls. The particle cannot actually be right at this spot, right? It's the potential sort of ill-defined there, and on top of that, it's, you've got that infinite force pushing it away from this point, right? And so it turns out the particle really can't be at this spot. And there's other reasons, too, that we'll get to later about the wave function has to be continuous, right? And if it were just, some value right at this wall and then jump to 0 here, right, it would not be continuous, right? So the wave function has to actually be 0 at the two boundary points in order for it to be continuous, in order for it to make physical sense, right? You can't have the particle have a probability of being at this one point right where the potential becomes infinite. Right? So in fact, this is a condition where x is less than or equal to 0, and where x is greater than or equal to a. And we could also write this, this implies that psi of 0 equals 0, and psi of a equals 0. And this will be important, right? And you'll see where we use this and what very interesting result those conditions give us. Okay, so now we know what the wave function is when we solve the right. We know what the wave function is between or negative infinity and 0 in between a and infinity, right? So really, we just need to solve the wave function for between x equals 0 and x equals a. So I'll write this here, and I'll write down the Schrodinger equation. So we have the Schrodinger equation between we want 0 is less than or yeah, I mean this might work for the less than or equal to. Whatever it doesn't actually make a huge difference. I'll just write less than, probably. Yeah, 0 is less than x is less than a, right? And then this also does imply, because we have to make sure it hits 0 at 0 and a. So considering we're using those conditions, it doesn't really matter if we include that. So that's more just semantics at this point. So now let's write down our Schrodinger equation between these points, though, right? Because when we're doing it, when we have the potential energy, we only need to talk about the potential energy between these points. We already know what the wave function is, just based on physics, right? Outside of the box, right? And so let's say we know negative h bar squared over 2m d squared, and we're going to be solving. Actually, we don't need a partial derivative, because we are going to be solving, remember, to get the general solution to the Schrodinger equation, we just have to solve the time-independent equation. So I'll just use a normal, ordinary derivative, d squared by dx squared psi e. Remember, we're looking for the energy eigenstates, plus v of x, right? But between these points, v of x is 0, so we can get rid of that, equals. And now we have e psi e, right? Okay, so the next thing that we are going to do, right, is we're going to rearrange this equation a little bit. So if we rearrange this equation, we want to get d squared by dx squared psi e equals minus 2m e over h bar squared psi e. And now we are going to make sort of a substitution. We're going to define this variable, or not a variable, it's a quantity. Sorry, it's not a variable, actually. We're going to define a quantity k, and k may seem kind of familiar to you, and you'll see it actually does correspond in a way to the wave number k. And we're going to say k is equal to root 2me over h bar, the h bar not inside the square root. Okay, so if we write it like this, we know that this then becomes, I'll put it over here, d squared psi e by dx squared equals negative k squared psi e. And we know how to solve this differential equation, that this is a differential equation we know how to solve. Now, we could write the solution, in fact, in one of two ways. We could write it as, some, like, a e to the I k x plus b e to the minus I k x. Or we could write it as some other, these can be, call it A1, where these are slightly different. A1 sine of kx plus A2 cosine kx. Right? And I think I showed in that video on differential equations that it actually, both ways are equivalent. This would be B1. I don't know why. Kx. This would be B1, right? These are just different labels, right? And we could use either one of them. Now, for this problem, because if you know where this is going, especially with these boundary conditions, and you've solved these differential equations, these kind of differential equations before, you will know which form we should use for this problem. And there will actually be another way. Now these are equivalent if we allow A and B to be complex, and A1 and B1 to be complex. But you'll find out, actually, in a few videos, that we should be using this one, and A and B will have to be real. And that's going to be a theorem that we'll look at in a few videos. But for right now, we still keep full generality, or yeah, for full generality, when we use the A sine plus B cosine. I'll just use A and B, right? So when we solve this equation, we can get that we know, let's put this in red here. We know this implies that psi e equals A sine kx plus B cosine kx. Okay, so now our next job is, and remember here A and B are constants, our next job is to plug in our boundary conditions, right? So let's look at our first one. Psi of 0, psi e of 0, right, has to equal 0, right? But psi e of 0 is A times the sine of 0 plus B times the cosine of 0, right? Because k times 0 is 0, right? Well, this has to equal 0. Now, A sine of 0 is 0, right? So we're left with B cosine of 0. Cosine of 0 is 1, right? So we are left with equation B equals 0, right? Which makes sense, because if there was a cosine and we were graphing it here, the cosine would have a point up here, right? That's how the cosine acts at x equals 0. It's not 0, right? So this actually, it makes sense that this has to be a sine wave, right? So now that we found that B equals 0, we are at psi e now equals A sine of kx. Right? Yeah, so we're psi e equals A sine of kx. Now we have our second condition, right? That psi e of A, little a, right, there's a big A and a little a, has to equal 0, right? But if we plug this in, this is capital A sine of K A equals 0. Now, we know that that has to mean, right, and I'm gonna erase, hopefully we have this down. I'm going to erase this stuff that we worked up out here. Make sure you have the stuff written down about how we use the boundary condition so we knew that this wave function had to be only a sine function, not a cosine. Now it should be more obvious why, right, because we couldn't have done that the same way, or as easily if we had used the e to the ikx, right? Okay, so since we don't want a to be 0, because if a equals 0, then the wave function is 0 everywhere, and that's, why even solve the problem, right? So from this, considering that we are really hoping that a is not 0, right, we can take from this. This means that, I'll put it up here, and I'm kind of working all over the place, but sine of kx equals, or sorry, not kx, ka equals 0, right? But sine of ka equals 0 if and only if, this means if and only if, right? And that's not, this sign means that it implies that sine of kx, or ka equals 0. That would mean that ka has to be a multiple of 2 pi. Or, no, just a multiple of pi, sorry. Right? That's the condition. Sine is 0 when its argument, when this thing inside, is a multiple of 2 pi. It is a multiple of pi. Right? And so we could write this as ka equals n pi, where n is a integer, right? 0, 1, 2, 3, 4, right? And now, right, we can rearrange this. We found actually a condition for A, or for K. So this means K equals n pi over A, right? And what that does in turn is if we plug back in our equation for K, and then we square both sides, right, and do the algebra, and hopefully you can do this on your own, what we'll end up with, if we solve for the energy E, right, once we solve for the energy E, we will get that E equals, right, again, plugging this back in, squaring both sides, multiplying by h bar squared, dividing by 2m, n squared pi squared h bar squared over 2ma squared, right? And this is our equation for the energies that this particle can have, right? And then our wave function that we have found, our wave function is, and I'm going to erase some of this, I'm going to actually erase our equation with k. I'm going to erase most of this. So yeah, most of this is gone, right? If we go back, I know I erased our wave function, but I think I'm writing in a slightly bigger pen font today, which is probably why I'm running out of more space than usual. We know what our wave function is. It's capital A times the sine of Ka, but K is n pi over little a, right? So we can also see here that our psi e, right, is capital A times sine of n pi over ax, right? So we have solved the Schrodinger equation. We've gotten the wave function, right, that corresponds to a definite energy, and they are these sine waves. And we'll get back to a little bit of what that means in a minute. Now, the first thing that I want to do is change a little bit of the notation here, right? Because now we don't just have an E, right? This is, we could write psi n, right? This is the nth wave function, and similarly, this is the nth energy level, where psi n just means it's a wave function with an energy E sub n, right? So whatever value for n you plug in, where n is 0, right? And I can actually write that n is 0, 1, 2, 3, ... right? And so this is our energy quantum number in this case. It's not the same for like the hydrogen atom, but it's a very similar idea, right? And the first thing to think about, and we will get back to this, and this is going to be a very big point, but notice, right, how did we get these quantized energies? We got them by plugging in these boundary conditions, and that's going to be a big point that we'll come back to in a little bit. Okay, so next, how do we figure out what this big capital A is, right? We're not given anything about capital A in the problem. We have to know, like, what the wave function is. We can't just have a random constant out there. And hopefully you know, right, the capital A we can determine by normalization, right? And so I'm going to erase our work here. Right, and so now all we have to do is plug in our normalization condition, where we have to normalize we have to normalize this wave function psi n. And I'll actually just keep it as psi n, see if we can come up with a general constant for normalization no matter which wave function we're looking at. Right? And so to normalize, and remember also normalizing our time-dependent equation solutions, right? if it's the capital psi e, and this only works if it's the capital psi e, right? This thing is normalized if little psi e is, right? And I showed that, I believe, 2 videos ago, right? So so it is important, really important, to normalize our psi n's, right? So our normalization condition is that the integral, now it's from negative infinity to infinity, but remember, we're doing that because we're integrating over all values of x, right? This wave function, and I didn't put it in there, but I kind of implied it with all this written up there, this wave function is only valid between 0 and a. Everything out, all the other times, it's 0, right? And so when we're integrating, right, if we think about the integral as like the area, right, psi squared, in any place where psi is 0, it's just going to be 0. So we're basically taking the area from negative infinity to 0 of under the 0, which is nothing, right? There's no area under that wave function. Then we'll have some area here and no area here because the wave function will be 0. So we can't get area between 0 and the x-axis because it will be on the x-axis. It's 0, right? The point that I was trying to say is all the area that we're integrating, right, is between 0 and a. You could also think about it as the normalization is summing. It's taking that integral over all possible x values. But in this problem, the only possible x values are between 0 and a. So when we're doing this normalization, instead of integrating from negative infinity to infinity, we could do that. But in order to do that, we'd still have to break it up. And in the end, we'd get an integral from x equals 0 to x equals a, right, over all possible values of x, of psi n norm squared dx. This has to be 1, right? And if we do this, now notice this wave function is real, and we can just say that, you know, let a be real, then we could multiply it by some phase, right? Remember, we can multiply by the phases to, you know, it will still keep the normalization, but just make it complex. So this is equal to, right, a squared. It could be a norm squared, but because there's really an infinite number, because we could just pick any complex number, right? We could just multiply this by any phase to get another good normalization constant. Hopefully you know what I'm talking about. If not, it's not a big deal. We'll say this is a squared, right? Because it's also a constant, so we can take it outside of the integral from 0 to little a, of sine squared of n pi over a x dx. Now, it turns out when you do this integral, right, when you do that integral, you get, in fact, something that does not depend on n, right? And this is not a general case. So in general, it could depend on n. But it turns out in this particular case, we get a squared times, and then when we do this integral, we actually get a over 2, little a over 2, right? But we know that this has to be equal to 1, right? And so if we solve for a, capital A is the square root of 2 over a. And now our wave functions are normalized. So let me plug that back in our equation here. Instead of this capital A, we have root 2 over a.